Chemistry influences every aspect of human life, be it the cleansing agents we use, the clothes we wear, the food we eat, or the medicines we take. Not just that, explosives, fuels, rocket propellants are also chemicals. Isn't it amazing that chemical reactions are the basis of life on Earth, and that all our activities are controlled by chemicals? In this unit, we will focus on the three significant areas where chemistry is largely applicable, namely drugs, food, and cleansing agents. Drugs are chemicals of low molecular masses that interact with macromolecular targets and produce a biological response. When the biological response is therapeutic, which means desired and beneficial, these chemicals are called medicines. The use of chemicals for obtaining a therapeutic effect is called chemotherapy. When drugs are taken in safe doses, they act as medicines and are useful in the diagnosis, prevention, and treatment of diseases. However, when the same drugs are consumed in excess, they act as potential poisons. However, never take drugs on your own. Always consult a qualified medical practitioner. Drugs can be classified on the basis of their pharmacological effect, drug action, chemical structure, and molecular targets. Drugs classified on the basis of their biological or pharmacological effects are useful in treating a particular type of problem. For example, analgesics have a pain-killing effect, whereas antiseptics kill or arrest the growth of harmful microorganisms. Drugs can also be classified on the basis of their action on a particular biochemical process. For example, antihistamines inhibit the action of the inflammation-causing compound histamine. Drugs classified according to their chemical structure share common structural features and often have similar pharmacological activity. For example, all sulfonamides have a common structural feature as shown here. Sulfonamides are antibacterial drugs used to treat bacterial infections. Drugs usually interact with biomolecules like carbohydrates, lipids, proteins, and nucleic acids. These biomolecules are called drug targets or simply target molecules. Drugs with similar structures have similar mechanisms of action on biomolecular targets. Drugs classified as per their molecular targets are especially used in the treatment of major ailments such as cancer and tumors. Have you ever wondered why the action of a drug is so specific? How can a drug be targeted at one specific biochemical function within the body? Let's try to answer these questions in this module. Biomolecules such as enzymes, receptors, carrier proteins, nucleic acids, lipids, and carbohydrates perform various functions in the body. Enzymes are proteins that act as biological catalysts in the body. Receptors are vital to the communication system in the body. Carrier proteins carry polar molecules across the cell membrane. Nucleic acids contain coded genetic information for the cell. Lipids and carbohydrates form the structural part of the cell membrane. The action of a drug depends on the interaction between the drug molecule and the biomolecule that it targets. In order to understand the interaction between drugs and enzymes, we first need to understand the catalytic action of enzymes. Every enzyme has a pocket known as the active site or binding site, which enables reacting molecules to bind to it. The reacting molecules are known as substrates. A substrate molecule has a shape complementary to that of the active site of an enzyme and fits into it just like a key fits into a lock. A substrate binds to the active site of an enzyme through a variety of interactions, such as ionic bonding, hydrogen bonding, van der Waals interaction, or dipole-dipole interaction. The enzyme then provides functional groups to react with the substrate and form products. As the products separate themselves, the active site gets vacated, ready to accommodate another substrate and continue the reaction. Drugs known as enzyme inhibitors can block the binding site of the enzyme and prevent the binding of a substrate to it, or inhibit its catalytic action. Drugs inhibit the attachment of a substrate on the active site of an enzyme in two different ways. One way is by competing with a natural substrate for attachment to the active site. Such drugs, known as competitive inhibitors, block the binding site to prevent a substrate from binding to the enzyme. The other way is by binding to a different site on enzyme, called the allosteric site. By doing so, it changes the shape of the enzyme's active site in such a way that a substrate cannot bind to it. An enzyme is blocked permanently if the bond it forms with an inhibitor is a strong covalent bond. In such a case, the body degrades the enzyme inhibitor complex and synthesizes the new enzyme. Now, let us see the drug-receptor interaction. The tissue constituent with which a drug is supposed to combine to produce a pharmacological effect is called a receptor. Receptors are important to the body's communication process. Most of them are embedded in cell membranes. The active site of a receptor extending out of the membrane receives chemicals known as chemical messengers, which pass messages between two neurons and between neurons and muscles. The active site of a receptor changes its shape slightly to accommodate a chemical messenger. Once the chemical messenger moves away from the receptor, the active site regains its original shape. Thus, the chemical messenger gives the message to the cell without entering it. There are a large number of receptors in our body. Each receptor shows selectivity for one chemical messenger over another. This is because the binding site of each receptor has a different shape, structure, and amino acid composition. Based on the interaction with receptors, drugs can be categorized into antagonists and agonists. Antagonists are drugs that bind to the active site of a receptor and inhibit its natural function. These are useful when a message is required to be blocked from reaching a cell. Agonists are drugs that behave like natural chemical messengers. They bind to receptors and activate them to produce the desired response. They are useful when there is a lack of natural chemical messengers. This is how a drug carries out a specific action and can be targeted at one specific biochemical function within the body. First, let us take a look at antacids. Your stomach produces acid to digest the food that you eat. It is mainly hydrochloric acid. Excessive secretion of the acid can lead to pain and discomfort in the stomach. If this happens regularly, it causes gastritis, which inflames the lining of the stomach. For many years, stomach acidity was treated by giving antacids such as sodium hydrogen carbonate or a mixture of hydroxides of aluminium and magnesium hydroxide. However, excessive use of antacids makes the stomach alkaline and triggers the production of even more acid. Metal hydroxides such as aluminium hydroxide, magnesium hydroxide or calcium hydroxide are a better treatment. This is because they are insoluble in water and do not increase the pH above neutrality. However, because of their mode of action, antacids address only the symptoms of excessive acidity, not the cause. A major breakthrough in the treatment of hyperacidity was the discovery that histamine, a potent vasodilator, also stimulates the secretion of pepsin and acid in the stomach. This discovery spurred the search of new compounds that structurally resembled antihistamines and would block acid secretion. Cimetidine is one such antihistamine drug designed to prevent the interaction of histamine with the receptors present in the stomach. As a result, less amount of acid is produced in the stomach. Ranitidine, which was discovered after cimetidine, is a more popular antihistamine drug. Histamine has a variety of actions, including the contraction of smooth muscles in the bronchi and gut, and the relaxation of other muscles, such as those in the walls of fine blood vessels. Histamines bind to the receptors in the nasal cavity. And cause blood vessels to swell and secrete excess fluid, causing sneezing and a running nose. Thus, histamines are also responsible for the nasal congestion associated with common colds and with allergic response to pollen, food products, dust, sheep wool, etc. Antihistamine drugs such as brompheniramine and terfenadine provide relief from the allergic effects of histamines by attaching themselves to the receptors. Thus, histamines are prevented from binding to the receptors and from causing chemical reactions that produce allergic symptoms. The next class of drugs is neurologically active drugs. Neurologically active drugs affect the message transfer mechanism between the nerves and the receptors. Neurologically active drugs are commonly classified as tranquilizers and analgesics. A tranquilizer is a drug that acts on the central nervous system. They are prescribed by doctors to treat anxiety, depression, tension, and sleeping disorders. These drugs reduce anxiety and promote calmness, relaxation, and sleep. There are several types of tranquilizers, like antidepressants and barbiturates. They function by different mechanisms. Let us now see how antidepressant drugs, which are a type of tranquilizers, help reduce depression. Tranquilizers slow down the normal functioning of the brain. For that reason, they are often referred to as depressants. These kind of drugs work by affecting the neurotransmitters. Neurotransmitters are brain chemicals that help brain cells communicate with one another by spreading nerve impulses from one nerve cell to another. Their complex interaction is what shifts our mood and changes our mind. For example, noradrenaline is a neurotransmitter that plays a role in mood changes. If the level of noradrenaline is low for some reason, then the signal sending activity becomes low, and the person suffers from depression. In such situations, antidepressant drugs such as iproniazid and phenelzine are used. They help correct the abnormal neurotransmitter activity by inhibiting the catalytic degradation activity of noradrenaline by enzymes. The relatively mild tranquilizer, namely 𝙁𝙈 helps relieve tension. Another tranquilizer, Equinil, is used to control depression and hypertension. Another important class of tranquilizers is barbiturates. It includes the derivatives of barbituric acid such as veronal, amytil, nembutyl, luminil, and seconil. Barbiturates are used as sedatives, that is, to produce a calming effect, and also as hypnotics, that is, to induce sleep. Other examples of this class are Valium and serotonin. Analgesics, commonly known as painkillers, reduce or remove the sensation of pain without causing any impairment of the nervous system. They are classified into non-narcotic and narcotic analgesics. Non-narcotic analgesics do not have addictive properties. Acetyl salicylic acid, commonly known as aspirin, is the most commonly used non-narcotic analgesic. Aspirin effectively relieves minor pains, inflammations, and fevers by inhibiting the synthesis of chemicals known as prostaglandins that stimulate inflammation in the tissue and cause pain. Aspirin also has anti-blood clotting action. And hence is useful in preventing heart attacks. Non-narcotic analgesics are also the most common pain relief medications used to treat osteoarthritis. Narcotic analgesics are the oldest as well as the strongest analgesics or pain-relieving drugs known to humans. Morphine, codeine, and many of their homologues are called narcotic drugs. They are also called opioids or opiates, as they are obtained from opium poppy. These drugs are addictive as they tend to produce a state of euphoria or a feeling of extreme well-being. When administered in medicinal doses, these drugs relieve pain and produce sleep. However, in high doses, they produce stupor, coma, convulsions, and finally death. These analgesics are chiefly used in relieving post-operative pain, cardiac pain, and pains of terminal cancer. Microorganisms such as bacteria, virus, and fungi cause different diseases in human beings and animals. Such disease-causing microorganisms are called pathogens. An antimicrobial is a substance that kills or inhibits the growth of these microorganisms. Antibiotics, antiseptics, disinfectants are antimicrobial drugs. First, let's learn about antibiotics. The word antibiotics comes from the Greek word anti, meaning against, and bios, meaning life. An antibiotic is a drug that kills or slows the growth of bacteria. Owing to their low toxic effect on humans and animals, antibiotics are widely used to treat bacterial infections. Bactericidal antibiotics kill bacteria, while bacteriostatic antibiotics inhibit the growth of bacteria. In the earlier days, antibiotics were defined as chemical substances produced by a microorganism, which inhibit the growth of or kill other microorganisms. With the advent of synthetic methods of production, purely synthetic antibiotics were produced. Hence, the definition of antibiotics has been modified. An antibiotic is now defined as a substance produced wholly or partly by chemical synthesis, which, in low concentrations, inhibits the growth of or destroys microorganisms by intervening in their metabolic processes. Synthetic antibiotic chemotherapy as a science and the story of antibiotic development began in Germany with Paul Ehrlich, a German medical scientist. He found that a compound that contained arsenic, arsphenamine, also known as salvarsan, was effective in the treatment of syphilis. His methodical search for a specific drug to treat a specific disease marked the beginning of targeted chemotherapy. The real revolution in antibacterial therapy began with the work of Alexander Fleming. He showed that molds such as the penicillium species can produce antibacterial chemicals. Fleming's discovery and the isolation of penicillin marked the beginning of modern antibiotics. Around the same time, the German bacteriologist 𝙤𝙊𝙃 announced that the red dye prontossil is active against certain bacterial infections in mice and humans. Soon afterwards, French scientists showed that the active antibacterial agent of prontossil is sulfalinamide. Further research has provided an overwhelming evidence of the efficacy of both frontosil and sulfanilamide in streptococcal septicemia. This marked the beginning of the sulfonamide era. Bacteria are grouped as gram-positive and gram-negative on the basis of the results of the gram staining test. Bacteria that stain purple are termed gram-positive, and those that stain pink, gram-negative. Antibiotics that kill or inhibit a wide range of gram-positive and gram-negative bacteria are said to be broad-spectrum antibiotics. Ampicillin, amoxicillin, chloramphenicol, vancomycin and ofloxacin are some such broad-spectrum antibiotics. Chloramphenicol is a bacteriostatic antibacterial that is rapidly absorbed from the gastrointestinal tract and, therefore, can be given orally in case of typhoid, dysentery, acute fever, certain forms of urinary infection, meningitis, and pneumonia. Narrow-spectrum antibiotics, on the other hand, are active against gram-positive or gram-negative bacteria, but not against both. Penicillin G is a narrow-spectrum antibiotic which is effective against gram-positive bacteria. Now, let's look at other antimicrobial drugs, antiseptics and disinfectants. An antiseptic is a substance that kills or inhibits the growth of microorganisms on the external surfaces of the body. Unlike antibiotics, they are not ingested, but are applied on living tissue, like on wounds, cuts, ulcers, and diseased skin surfaces. Let us look at some examples of commonly used antiseptics. A tincture consisting of a solution of elemental iodine in ethyl alcohol water mixture is known as tincture of iodine. It is applied topically to wounds as an antiseptic. Bithionol is added to soap to impart antiseptic properties. Dettol, a mixture of chloroxylenol and terpineol, is an inexpensive liquid antiseptic. Iodoform, an organoiodine compound, is used as an antiseptic for wounds. A dilute aqueous solution of boric acid is used as a weak antiseptic for the eyes. Disinfectants are antimicrobial substances used on non-living objects such as floors, drainage systems, and instruments. Disinfectants are frequently used in hospitals, dental surgeries, kitchens, and bathrooms to kill infectious organisms. Chlorine in the concentration of 0.2 to 0.4 parts per million in an aqueous solution is used as a disinfectant. Similarly, a sodium hypochlorite solution is used to disinfect drains and toilets. A substance can act as an antiseptic as well as a disinfectant just by varying its concentration. For example, phenolics are active ingredients in some household disinfectants. A 0.2% solution of phenol acts as an antiseptic, while a 1% solution acts as a disinfectant and is used to clean floors. Another important type of drugs is anti-fertility drugs. With global population growing by the day, birth control has become essential. Oral contraceptives or anti-fertility drugs are used for birth control. Birth control pills essentially contain a mixture of hormones, namely synthetic estrogen and progesterone derivatives. Progesterone is known to suppress ovulation. Norethindrone is a synthetic progesterone derivative most widely used as an anti-fertility drug. Another drug, novestrol or ethinyl estradiol, uses an estrogen derivative in combination with the progesterone derivative. Chemicals are added to food for various reasons, such as enhancing its appeal or nutritional value and to preserve it. There are various categories of food additives, namely food colors, flavors and sweeteners, fat emulsifiers and stabilizing agents, flavor improvers, antioxidants, preservatives, and nutritional supplements such as minerals, vitamins, and amino acids. Note that, except for nutritional supplements, none of the additives mentioned have any nutritional value. They are added either to prolong the time for which food can be stored or just for cosmetic purposes. Among these, let us take a look at the use of sweeteners and food preservatives. A sweetener is a food additive that adds the basic taste of sweetness to food. Natural sweeteners like sucrose, maltose, glucose, and honey add calories when consumed. On the other hand, artificial sweeteners like aspartame, 𝙁𝙁𝙋𝙇, saccharin, and sucralose are basically non-nutritive sugar substitutes, as they provide no calories when consumed. Hence, they are popular among diabetic and diet-conscious people. Let us take a look at some common artificial sweeteners. Saccharin is one of the most popular sweetening agents, which is used to sweeten products such as drinks, candies, medicines, and toothpaste. It is about 550 times sweeter than cane sugar, that is, sucrose, but has an unpleasant bitter or metallic aftertaste, especially at high concentrations. Another popular and widely used artificial sweetener is aspartame. Aspartame is a methyl ester of the dipeptide formed from the amino acids aspartic acid and phenylalanine. It is a non-saccharide sweetener that is about 200 times sweeter than cane sugar. It has a sweet taste without the bitter chemical or metallic aftertaste reported in other artificial sweeteners. However, its use is limited to cold food and soft drinks as it is unstable at cooking temperature. The artificial sweetener 𝙁𝙁𝙃 is a dipeptide of the amino acids aspartic acid and alanine. Attached to the alanine moiety is a novel amine that is presumed to be responsible for the elevated sweetness potency of 𝙁𝙁𝙃. 𝙁𝙁𝙃 is about 2,000 times sweeter than sucrose, has no aftertaste, and is more stable than aspartame. As it is a high-potency sweetener, it is difficult to control the sweetness of food when it is used as an artificial sweetener. Sucralose is a trichloro-derivative of sucrose and a zero-calorie artificial sweetener, which looks and tastes just like sugar. Sucralose is approximately 600 times sweeter than sucrose and is stable at cooking temperature. It is a very versatile sweetener that is used in a wide variety of foods and beverages. Now, let's learn something about food preservatives. A food preservative is a naturally occurring or synthetic substance added to food to prevent spoilage by microbial growth or undesirable chemical changes. Food preservation is basically done for three reasons: to preserve the natural characteristics of food, to preserve the appearance of food, and to increase the shelf life of food for storage. Natural substances such as salt, sugar, vinegar, and vegetable oils are traditional preservatives often used to prepare pickles and jams. Sugar and salt are the earliest natural food preservatives that very efficiently inhibit the growth of bacteria in food. Artificial or chemical preservatives are either added to food or sprayed on food and have been known to effectively prolong the shelf life of food. Artificial preservatives act as either antimicrobials or antioxidants, or both. Antimicrobials in preservatives prevent the growth of molds, yeasts, and bacteria, while antioxidants keep food from becoming rancid. Antioxidants also prevent the loss of some essential amino acids and vitamins. Some examples of chemical food preservatives are benzoates, nitrites, and sorbates. Sodium benzoate protects food against yeasts and molds and is used in jams, beverages, salad dressings, pie and pastry fillings, etc. Sodium nitrite is used to fix the colors in preserved fish and meat. The sorbate family of compounds available as sorbic acid, potassium sorbate, sodium sorbate, or calcium sorbate are effective against yeasts, molds, and selective bacteria, and are widely used in cheese, dips, yogurt, bread, icings, salads, beverages, olives, smoked and salted fish, and several other food items. The word detergent is a general term used to denote a cleansing agent. Two types of detergents, namely soaps and synthetic detergents, are used as cleansing agents. These agents improve the cleansing properties of water. They help remove the oily and fatty substances that bind dirt and other material to the skin or the fabric. Soaps used for cleaning are sodium or potassium salts of naturally occurring long-chain fatty acids such as stearic, oleic, and palmitic acids. Soaps that contain sodium salts are formed by heating oil or fat of vegetable or animal origin, which is a glycerol ester of a fatty acid, with an aqueous sodium hydroxide solution. The hydrolysis of oil or fat results in the formation of a mixture of a sodium salt of a fatty acid and a glycerol, as shown in the equation here. As the salts thus formed are used as soaps, the alkaline hydrolysis of oils and fats is commonly known as saponification. In this reaction, esters of fatty acids are hydrolyzed and the soap obtained remains in colloidal form. The soap and the glycerol are separated by adding concentrated sodium chloride solution to the mixture. The glycerol dissolves in the salt solution, but the soap is insoluble and hence floats on the surface of the solution from where it is removed. Glycerol from the solution is recovered by fractional distillation. Potassium soaps, produced by the saponification of fats with potassium hydroxide, are usually softer and more soluble than sodium soaps. Soaps may vary in composition and method of processing. For example, substances of medicinal value are added to medicated soaps. Similarly, glycerol and a gum called rosin are added while preparing shaving soaps. Glycerol prevents rapid drying, while rosin forms sodium rosinate that lathers well. Similarly, laundry soaps contain fillers like sodium rosinate, sodium silicate, borax, and sodium carbonate. Transparent soaps are made by dissolving the soap in ethanol and then evaporating the excess of solvent. Soaps that float on water are made by beating air into them before they harden. In preparing soap powders and scouring soaps, an abrasive agent such as powdered pumice or finely divided sand are added, along with builders such as sodium carbonate and trisodium phosphate. The builders enable the soap to act at a faster rate. In preparing toilet soaps, good quality fats and oils are used, and excess alkali is removed. Perfumes and colors are added to make them attractive. Soaps are good cleansing agents, but they do not work with hard water. Hard water has high mineral content that primarily consists of calcium and magnesium ions. These ions make the water resistant to soaps. When these ions come into contact with sodium or potassium soaps, they form insoluble calcium and magnesium soaps, thus rendering them useless as cleansing agents. Calcium and magnesium soaps form a white precipitate called scum in water and hinder cleaning by sticking to the cloth fiber, skin, or hair, thus preventing the formation of lather. Let us now look at synthetic detergents. Synthetic detergents are cleansing agents that have all the properties of soap but do not contain any soap. They are more efficient than soaps as they give foam in soft water, hard water, as well as in ice-cold water. Synthetic detergents are classified into three main categories. These are anionic detergents, cationic detergents, and non-ionic detergents. Anionic detergents are sodium salts of sulfonated long-chain alcohols of hydrocarbons. Treating long-chain alcohols with concentrated sulfuric acid yields alkyl hydrogen sulfate. Neutralizing alkyl hydrogen sulfate with an alkali gives an anionic detergent. Similarly, alkyl benzene sulfonic acids, on being neutralized with an alkali, yield alkyl benzene sulfonates as shown in the reaction here. In an anionic synthetic detergent, the anionic part of the molecule does the cleansing action. Anionic detergents are used extensively as dishwashing liquids, laundry liquids, and powder detergents, car wash detergents, and shampoos, as well as in toothpastes. Cationic detergents are quaternary ammonium salts of amines with acetates, chlorides, and bromides as anions. The cationic part has a long hydrocarbon chain with a positive charge on the nitrogen atom. Hence, these are called cationic detergents. Cetyl trimethyl ammonium bromide, which is used in hair conditioners, is a well-known cationic detergent. Being expensive, their use is very limited. Non-ionic detergents do not have any ions. Therefore, they are resistant to water hardness deactivation. They produce electrically neutral colloidal particles in solution. The reaction between stearic acid and polyethylene glycol to yield a non-ionic detergent can be seen in the equation here. The liquid dishwashing detergents that we use are of the non-ionic type. Their mechanism of action is the same as that of soaps. Non-ionic detergents are excellent grease removers that are used in laundry products, household cleaners, dishwashing liquids, and even cosmetics. One of the dangers posed by detergents is their extremely slow rate of degradability. This is because their hydrocarbon chain is highly branched, which makes it very difficult for bacteria to degrade it. As a result, the detergents go on accumulating. Ultimately, when they reach water bodies, they cause pollution and foaming. This problem persists despite the treatment of polluted water. Therefore, currently, research is being conducted to control and minimize the branching of the hydrocarbon chain in order to make detergents more easily biodegradable.